Let's do a complete worked example using the method of mixtures. Suppose we have a sample of a biological material. The sample mass is 1/10 of a kilogram, and the sample is initially at 70 degrees Celsius. Now we have water in the calorimeter. The water mass is 2/10 of a kilogram, and the water is initially at 20 degrees Celsius. We place the hot sample into the water, we stir gently, and after the temperature stabilizes. The final equilibrium temperature is 25 degrees Celsius. Our goal is to determine the specific heat of the sample. The key idea is that the heat the sample loses is equal to the heat the water gains. As long as the calorimeter is well insulated and we ignore the heat absorbed by the container for this simplified example. So we will calculate how much heat the water gained from warming up, and we will set that equal to how much heat the sample lost while cooling down. First, look at the water. The water started at 20 degrees Celsius and ended at 25 degrees Celsius. So the water warmed up by 5 degrees. Now look at the sample. The sample started at 70 degrees Celsius and ended at 25 degrees Celsius. So the sample cooled down by 45 degrees. We will use the known specific heat of water, which is approximately 4.187 kilojoules per kilogram per degree. For simplicity, we would assume no other heat loss and no calorimetric constant. Heat gained by the water equals the water mass multiplied by the specific heat of water multiplied by the water temperature increase. Now substitute the values. The water mass is 2/10 of a kilogram. The specific heat of water is 4.187 kilojoules per kilogram per degree. The temperature increase of the water is 5 degrees. Now multiply step by step. First multiply 4.187 by 5. That gives 20.935. Now multiply that by 2/10. 2/10 of 20.935 is 4.187. So the water gained 4.187 kilojoules of heat. Now we write the heat lost by the sample in the same form. Heat lost by the sample equals the sample mass multiplied by the sample's specific heat multiplied by the sample temperature decrease. The sample mass is 1/10 of a kilogram. The sample temperature decrease is 45 degrees. The sample's specific heat is what we are trying to find. So, in words, the heat lost by the sample equals 1/10 of a kilogram multiplied by the unknown specific heat, multiplied by 45 degrees. Now we set the heat lost by the sample equal to the heat gained by the water. We already calculated that the water gained 4.187 kilojoules. So we set 1/10 times the unknown specific heat times 45 equal to 4.187 kilojoules. Next, multiply 1/10 by 45. 1/10 of 45 is 4.5. So now we have 4.5 times the unknown specific heat equals 4.187. To isolate the unknown specific heat, divide 4.187 by 4.5. 4.187 divided by 4.5 is approximately 0.93. So the specific heat of the sample is approximately 0.93 kilojoules per kilogram per degree. Now interpret what that number means. This value is much lower than the specific heat of water, which is around 4.187. A specific heat near 0.93 suggests the sample behaves more like a low moisture solid or a material with a lot of fat or dense dry matter, rather than a high moisture biological product. If this sample were something like a fresh fruit or vegetable, we would expect a much higher value, typically closer to 3 or 4 kilojoules per kilogram per degree. In a more careful experiment, we would also include the heat absorbed by the calorimeter container, thermometer, and stirrer. That would slightly change the result. But the structure of the method is exactly what you saw. Measure masses and temperatures, compute the heat gained by the reference fluid, equate it to the heat lost by the sample, and solve for the unknown specific heat.